Levenshtein distance becomes a full vocabulary scan, unless a BK tree prunes impossible typo candidates. You'll implement a BK tree using Levenshtein distance to return bounded radius typo candidates and the number of comparisons performed. I'm Professor Pi, teaching search and IR with simple Python. A search box should handle bok when the vocabulary contains book. The simple solution compares that query with every term. That works for a tiny list. But each new query repeats the same costly scan. A BK tree organizes terms so many comparisons never need to happen. The goal is not to guess the best document yet. It is to quickly find plausible corrected terms. Those candidates can then move into normal search ranking, filters, or another relevant stage. A typo search needs a clear boundary. If we allow one edit, bok can match book, but terms that are clearly farther away should be ignored. The BK tree uses distances already measured during insertion to decide which parts of its vocabulary are worth visiting. We will build a small term index that stores words by edit distance. Then we will search it with a radius and count the distance checks. That count makes the pruning benefit visible instead of treating it as magic. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We first need one reliable way to measure how different two terms are. This snippet computes Levenshtein distance, which is the minimum number of single character insertions, deletions, or substitutions needed to change one string into another. The function named lev builds one dynamic programming row at a time from prev, rather than keeping a full table in memory. That is enough, because each new row only needs the one before it. The query is bok, and the term is book, so the missing character creates an edit distance of 1. The printed edit distance confirms that this pair sits inside a typo radius of 1. Every later tree decision depends on this metric being consistent. One distance is useful, but we need a place to remember where terms sit relative to each other. This example creates the first distance-keyed connection in the BK tree. A normal binary tree only asks whether one value is smaller or larger. That cannot represent how many edits separate two words. Each node instead keeps children in kids, with an integer distance as the key. The root stores book, and books becomes a child under the edge calculated by lev. The small terms list stands in for a searchable vocabulary, such as product names or document tags. The printed inserted edge confirms that the first child landed in distance bucket 1. That bucket means every term below it has a specific relationship to its parent. A single edge proves the structure, but a usable index must keep inserting when a distance bucket is already taken. This code turns those individual edges into a reusable term index. The add function measures the incoming term against the current node. If that distance key is unused in kids, it creates a new node there. If the edge already exists, add follows that child and measures again from the new location. It continues until it finds an open bucket. This keeps one child per edge value while allowing many terms to form deeper branches. The insertion order matters because it changes the tree shape, and that can change later traversal work. The printed root edges shows that the root splits this vocabulary into two initial distance regions. For more practical search and IR lessons, subscribe and keep building these ideas with me. The tree is ready, so the next need is skipping branches that cannot possibly contain a close correction. This snippet searches the BK tree while pruning distance buckets that cannot hold valid candidates. At each node, search calculates dist from the query to that term. It keeps the term when dist is within radius. Then, it only visits child edges from low through high, based on the current distance and the allowed radius. The triangle inequality makes this safe. An edge outside that interval cannot lead to a term close enough to the query. Increasing radius usually returns more candidates, but it also opens more branches and comparisons. Decreasing it narrows traversal and can miss looser typo matches. The printed candidates and comparisons show a valid correction after checking only part of the 7-term vocabulary. One query demonstrates pruning, but retrieval code usually needs to process several misspellings and report the savings. This example packages the tree search into a small batch retrieval baseline. Each value in queries goes through search with radius 1. The matches result removes the distance values while preserving the deterministic ranking from sorted hits. The check saved value compares visited nodes against a brute force baseline, where lev would run for every query term pair. That makes the result practical to inspect, not just theoretically correct. In a retrieval pipeline, these candidates can feed lexical scoring, metadata filtering, or hybrid re-ranking, rather than replacing relevance ranking. The visible output shows useful typo candidates for both queries and the edit distance comparisons avoided. When a vocabulary is small or changes constantly, a direct scan can still be the simpler choice. It has predictable behavior and no tree building step. A BK tree becomes attractive when many typo queries reuse a stable term dictionary, and exact edit distance is important enough to justify an index. This example shows the central trade-off clearly. The tree does not eliminate Levenshtein work. It avoids work in regions that cannot produce an answer inside the chosen radius. Its effectiveness also depends on the vocabulary and insertion order. So measure comparisons on representative terms rather than assuming every tree prunes equally well. Try changing the radius from 1 to a larger value and watch both the candidates and comparison count. You can also compare different insertion orders to see how the same terms create different tree shapes. What practical search or IR topic would you like to explore next? Share it in the comments and subscribe for more clear Python retrieval lessons.